This is a lesson on simple harmonic motion and a unit on simple harmonic motion and waves. Simple harmonic motion is a basic conceptual and mathematical model used in physics that arises from the spring model of materials. It describes motion of particles and waves. It's such a useful model because of this. Motion of particles and waves. So when I look at the examples I have on this page that I've gathered together, here's molecules and waves. Here's a sound wave. It's a longitudinal wave as opposed to a transverse wave, which you can see with the guitar or the slinky here. Also, here's a mass on a spring. That's something that exhibits simple harmonic motion. Here's a pendulum that goes back and forth. If the theta is small enough, I get simple harmonic motion there. Here's circular motion. You can see uniform circular motion is an example of simple harmonic motion because it's periodic. When something moves in a circle, I can see that the mathematical model of it created by impression on a sheet of paper looks like an actual physical wave, an actual physical entity that has periodic motion. The other example that I brought up that will be important as you move towards quantum is the quantum harmonic oscillator. Here I have a diatomic molecule that oscillates. Its energy oscillates as a spring with spring potential energy. And actually with quantum harmonic oscillators, that energy is quantized. So you can see the equation here. So we see that this model is useful in so many places in physics. So let's establish a good understanding of what it is. First, I need to talk about properties of oscillatory or periodic motion. And it may seem, if you're familiar with these terms, it may seem self-explanatory. Periodic motion consists of cycles or patterns that are produced over and over again by the source, and these are represented by sinusoidal functions. We talked about this initially with rotational kinematics. When something is moving in a uniform circle, uniform circular motion, it has a period. And so you see that's one of the characteristics of simple harmonic motion is that there is a period. There's some cycle and amount of time that the same motion happens over with the same time, the same amount of time, the same amount of time. The model that is used in this situation, the simplest archetype to just lay down, here's a way to think about this, is with a mass on a spring. And I've chosen an example from OpenStax College Physics on page 676. Of just a mass on a spring oscillating up and down. It's a vertical spring. And what you also see on this is that there's an amplitude. With oscillatory or periodic motion, there's an amplitude, so that's how far it goes from its center position. We have been talking about springs, about how there's an equilibrium position, and so harmonic motion will have an amplitude around that equilibrium position. So we call that the maximum displacement of medium from the undisturbed position, and usually that's measured in meters. Period will be in seconds. And so we talk about frequency and angular frequency. These are important quantities as we move forward in harmonic motion and towards waves to talk about the frequency of a motion. Frequency is simply 1 over the period. It has thus units 1 over seconds, which we simplify to hertz. So that, to me, represents the number of cycles completed in 1 second. How many cycles get completed in 1 second? Angular frequency, and remember this relates to the circular motion. When I think about something completing a cycle, things can go in a circle and complete a cycle. That's where we started, rotational kinematics. That this angular frequency can thus be used for an object like a mass on a spring that isn't even exhibiting circular motion. I'm going to acknowledge to you right now that it doesn't make sense for a spring to be described as completing radians per second because it's not moving in a circle. The radians that we are completing in there is considered part of the cycle from 0 to 2 pi or 0 to 360 of a period. how fast is that object completing a cycle? So when we think about that, we want to know the number of radians traveled in 1 second. How fast is it completing that cycle in 1 second, represented by radians? And again, you may need to watch out in your calculator that you have degrees or radians going on. I will point out to this in applications as we move towards it. And keep your units in mind here. I wanted to just practice calculating period and frequency and get used to reading this information in the problem. So there's the equation that I had. Frequency is 1 over a period, and I can relate that to the angular frequency simply with that equation. The first thing I picked out here for us to work on is what is the frequency of the second hand of a clock, the minute hand, the hour hand. So we're looking at hands of the clock. All right. The second hand of the clock takes 60 seconds to go around. So T1 is 60 seconds. So if I want to calculate the frequency of the second hand, I would go 1 over the period, which is 1 over 60 seconds, and just call that hertz. And that's it. That's how you find the frequency. This is not angular frequency. This is plane frequency. In the second situation, the period, it wants the period of the minute hand. Well, it takes an hour for the minute hand to go all the way around. I know that's 60 minutes, which is 3,600 seconds. So when I find the frequency of the minute hand, I'll have 1 over 3,600 hertz. And that's the frequency of the minute hand. You're getting the hang of this. The frequency of the hour hand. Well, if you're looking at a regular clock, it takes 12 hours for the hour hand to make 1 complete revolution. So 12 hours in times 3,600 seconds per hour, this turns out to be 43,200 seconds. So when I calculate the frequency of the hour hand, we can see that it takes much longer for that hour hand to make 1 revolution. And so it's going to have a lower number of hertz than something that's moving faster around. It completes a cycle in a faster amount of time. So that's how you find frequency from period. Part B here says, if your heart rate is 150 beats per minute during strenuous exercise, what is the time per beat in seconds? So when I see time per beat, and it wants it in seconds, I think of that as a period, right? Period is given in seconds. Period is 1 over the frequency, but I'm going to do a little bit more like unit analysis here. I want how many seconds does it take for 1 beat? What is the time per beat? Seconds per beat. So they tell me in 1 minute, so 60 seconds, the heart beats 150 times. So I will write that out here, beat. Okay. When I simplify this, I get 0.4 seconds per 1 beat. The last question here, it says the frequency of the middle C on a typical musical instrument is 264 hertz. What is the time for 1 complete oscillation? So if I think about maybe that guitar string, how long does it take for that guitar string to oscillate at a middle C at 264 hertz? Well, the period, the time for 1 oscillation is the period. The period will equal 1 over the frequency, so I'll have 1 over 264 hertz, or 1 over seconds. I'm just doing the unit analysis here, right? Hertz is 1 over seconds, so I can put that in there, and you can see I'm going to get a timeout. This is actually 3.78 repeating times 10 to the negative third seconds, which I'm going to round to about 3.8 milliseconds. Super short time, really fast vibrating back and forth. Okay, so that's how I relate period and frequency. I wanted to return to the mass on a spring model that is the anchor for understanding simple harmonic motion, and this is what is defined as a simple harmonic oscillator. Again, when I think about quantum oscillators, that's what this model is, the simple harmonic oscillator. And it's a system where the net force can be described by Hooke's law. That's what it's defined as. That's a simple harmonic oscillator. Notice that a simple harmonic oscillator exhibits simple harmonic motion, but it's not the only thing that exhibits simple harmonic motion. There's so many things that exhibit simple harmonic motion. So what we're going to assume is that the spring is ideal, so this stays with the force is linear over displacement, and that there's no dissipative outside forces. You will see sections in the text that talked about damped motion, and you may study that further in this class or in another class. But for now, I'm going to keep this as assuming that I'm not losing any energy. Remember, we talked about spring potential energy. I'm not losing any energy to any outside sources. And typically, this comes from like air resistance, which is minimal to begin with anyway. And also any heat that's created in that spring deforming repeatedly as it oscillates back and forth, we're not going to lose any heat there. There's no dissipative outside forces going on. We're going to assume, and this is true for horizontal and vertical orientations. Notice in this picture I have a horizontal orientation of the spring rather than the vertical one I had on the prior slide. This mass oscillates back and forth in a repetitive motion, and it has a period t, which I can relate to a frequency and also its angular frequency. Its angular frequency is a very simple equation. It arises from you do some calculus and hand waving on Newton's second law equation, which is another math lecture that I've left for another time. And what you need to know is that the oscillation frequency, how quickly that mass completes a complete revolution, is related to the parameters in the problem, right? It should make sense that it depends on the spring constant. If that spring is stiff or if it's a stretchy spring, that will determine how fast it moves back and forth. The other thing it depends on is the mass. If it's a larger mass, it will just move slower. It's just the nature of it, and that is probably intuitive for you. Notice also that omega is in radians per second. So we're still thinking about completing cycles. No, the mass is not moving in a circle. It is completing cycles as if it were moving in a circle. So that's why we use radians in there. So we're going to use this equation in the next example, where I've chosen a situation where we have some sort of initial frequency, adding mass. A spring stretches by 0.018 meters when a 2.8 kilogram mass is suspended from its end. How much more mass should be attached to the spring so that its frequency vibration is 3 hertz? F to be 3. And we see F is up here in the omega equation. So I'm going to say that F equals 3 hertz and omega equals 2 pi F. I'm given a displacement and I'm given a mass and I'm given this frequency. So I know omega, and omega is related to the mass. So I'm going to think about it this way. The mass that I want to solve for, I can relate to the omega. So m equals omega squared k. And this m that I'm looking for, this m final, is going to be the initial mass plus some additional mass that they're asking us to find. That's what we don't know here. The initial mass is the 2.8, but I don't know the additional mass. That's what they're asking. So mass final equals omega squared k. I'm going to plug that in here. M initial plus m additional equals omega squared k. And so I'm solving for m additional. M additional is going to be omega squared k minus m initial. Okay, I know m initial. I don't know k though. K is a value that I am not given in the problem. Omega I'm okay with too, because I can just plug in 3 in here and that would give me an expression for omega. So I need to work on a value for k. I haven't used delta x yet. Notice I haven't used delta x. Delta x is 0.018 meters. And in the situation where I just have, I place that mass on the spring and it stretches, there's the spring force upward and there's the force of gravity downward, which I know is mg. And when I think about just setting that mass on the end of that spring, I'm going to get that the acceleration is 0. So I can do the same thing with Newton's second law here that I've done before. F net equals ma. The net force on here, I have the force of the spring upward minus the force of gravity downward, and that has to equal 0. So I get this relationship. K delta x equals mg. And I'm going to plug what I know about K will be mg over delta x, into this equation up here where I see K. So let me get this going. Omega I know is 2 pi times the frequency, and I need to square that term. K is given by this value, m initial times g divided by the delta x, and then subtract m initial. And it seems like I'm ready to plug numbers in. I know everything in here. 2 pi times 3 quantity squared. M initial is 2.8. I'm going to multiply that by 9.8, divide by the displacement, and then subtract 2.8. And make sure you do all of this stuff here first before subtracting 2.8. When you run this stuff through the calculator, you get 2.490522, and then I'm going to subtract 2.8 from that. And the additional mass that I need to add is 1.491 kilograms to get it from whatever it was, whatever the frequency was before, to this 3 hertz that I was aiming for. So that's the answer there. I wanted to highlight a few things here. I was glad that this was a larger number than the 2.8. I don't want to get a negative number here. It doesn't make sense that I have to subtract away from the mass when it tells me that I needed to add more mass. So that sign assured me that I was on the right track. The other thing, again, is that I'm using what I know from prior knowledge, right, the force of a spring, in order to get some information from delta x or k and relate it into this new material that I have about oscillating. So you're going to see that your old material, this review material, from old units will still keep coming up in working with spring stuff. And we'll see that with spring potential energy in a future lesson.